Today we're going to talk about the gas laws. Okay, and what I have in this can right here is I have some water. And you saw this demo already in class. Also in the can I have air, right, which is a mixture of gases. Okay, so what I'm going to do is I'm going to heat up the water in this can, and that means that the water, the liquid water, is going to be evaporating, forming water vapor. So water in its gas phase. Okay. Oh yeah, things are looking real good here. So, I've got some ice cold water here. My water is evaporating, so I've got some water vapor in there along with some liquid water. Alright, let's do this thing. Wow. What happened? Well, we're going to use gas laws to explain what happened right here. Was it me? No, it wasn't me. It was gases. So we're going to talk about 4 of them and do lots of practice with them. Okay, so the first one is Boyle's law. And Boyle's law tells us that volume is inversely related to pressure. So if we think about these things, they're kind of common sense. So for instance, when I say the volume is inversely related to pressure, and we'll do all kinds of fun stuff that's going to illustrate this. As the pressure on a gas gets less and less and less, as the pressure decreases, so the amount that you're pressing on the gas gets less and less and less, what do you think is going to happen to the volume of that gas? The volume of that gas is going to increase. Conversely, if you have a sample of gas and you are pressing on it, pressing on it, pressing on it, what's going to happen to the volume of the gas? It's going to decrease. So the two are inversely related with one another. And so this is the formula that we use. P1 times V1 equals P2 times V2 to solve problems in terms of pressure and volume. So let's do a problem on the board. What is the resulting pressure when 25.3 liters of gas at 3.20 atmospheres is compressed to 15 liters? So we're going to begin with a pressure of 3.20 atmospheres. So we start with 25.3 liters, and the pressure of the gas when it is in a container that is giving it 25.3 liters of space to occupy, that pressure is going to be 3.20 atmospheres. Well, what if we take that volume and we compress it to 15 liters? What's going to happen to the pressure of that gas? Well, first of all, if we decrease the volume of that gas, what's going to happen to its pressure? It's going to increase. It's going to go up. So let's plug into this so that I'm sure you can plug into it and solve for this. Alright, you guys, so let's go for this. So P1 times V1 equals P2 times V2. Use a black pen. Okay, so what is my initial pressure? What does my pressure start at? It starts at 3.20 atmospheres. So P1 is equal to my initial pressure, 3.20 atm. Okay, V1, what is my initial volume? My initial volume is 25.3 liters. Okay, what is P2? I don't know. That's what I'm looking for. That's my unknown. And V2, okay, so my end volume is 15.0 liters. All right, you guys, I'm plugging and chugging here. I'm just going to simply say 3.20 times 25.3 is equal to my unknown times 15.0. Okay, so what am I going to do here? I'm going to multiply these two together, divide that product by 15.0, and what am I going to get? I don't have a calculator because I'm borrowing mine for calculus. And no, I don't have an answer. So you guys can tell me what the answer is tomorrow. Multiply, it's algebra. Multiply them together, and then divide by 15.0, and that is going to give me my resulting pressure in what unit? ATM. We have Charles' law. That tells us that volume is directly proportional to temperature, meaning that as one goes up, so does the other. So as the temperature of a gas gets higher and higher, the volume of that gas will also do what? The volume of that gas will also decrease. So in terms of a formula, I'll go back, is that V1 over T1 is equal to V2 over T2. Okay. They are directly proportional to one another, directly related. Okay, so I'm going to go back up here and say, now that means that as the temperature of a gas decreases, the volume of that gas will also do what? Decrease. Okay, now I have this really interesting thing for you to think about. I think it's interesting. We'll see what you think. Okay, yeah, I made this graph, and okay, so it's a little bit yucky, but, you know, it's going to get the point across to people. All right. So think about this. Temperature is in degrees Celsius. Volume is in liters. So, what some chemists did, physicists, was they took a sample of different gases. Dinitrogen oxide, hydrogen gas, water vapor, methane, helium. And what they did was they cooled those things down. Okay, so they just decreased the temperature, decreased the temperature, decreased the temperature, decreased the temperature, decreased the temperature. Now, at the time they did that, initially, they couldn't really get a whole lot cooler than this. Okay? So that this part of the graph is an extrapolation. And no matter what the nature of the gas is that as you cool it to a certain point, and you extrapolate these lines, they all extrapolate to this same point on the x-axis. That point is negative 273.2 degrees Celsius, also known as 0 Kelvin, absolute zero. Have we ever gotten anything to absolute zero? No, we have not. We have tried and tried and tried. And they are trying now. Very difficult. Because at this temperature, theoretically, all motion ceases. No more motion. At absolute zero. 0 Kelvin. What if we got something below 0 Kelvin? What if we actually got the temperature even lower? Okay, then what happens? What happens below here, you guys? What do we have? Negative volume? What does that mean, negative volume? But apparently, one would think that if we can get below 0 Kelvin, volume is going to disappear? I don't know. Think about it. Okay, so that's what I mean by this. The volume of a gas extrapolates to 0 when the temperature is 0 Kelvin. Okay, so we say that 0 Kelvin is absolute zero. And we use Kelvin as the unit for all gas law problems. So whenever we're reporting temperature, our unit is always going to be in Kelvin because that's where the proportionality is correct. It is not correct when we are using Celsius. Things are not directly or inversely proportional. They are only directly or inversely proportional linearly when we use Kelvin as our unit. So it's really easy to change from Celsius to Kelvin. So we add 273. So 35 degrees Celsius, what is that in Kelvin? Well, you guys, it's 273 plus 35. And that will give us our temperature in Kelvin. So whenever we are solving here, we always have to use Kelvin for our temperature. It doesn't matter if we use in this, we can use liters, we can use milliliters, and that would be all right. It has to be Kelvin. Okay. I'm just rolling through these really fast. Gay-Lussac. That's how you say it, Gay-Lussac. Pressure is directly proportional to temperature. Meaning, as the temperature of a gas increases, what happens to its pressure? Well, if it's directly proportional, that means as the temperature goes up, so goes the pressure. So as you increase the temperature on a gas, the pressure of that gas is also going to go up. Vice versa. There is our formula. P1 over T1 equals P2 over T2. ATM here, we have to use ATM here. If we use millimeters of mercury here, we have to use millimeter. Our answer will come out as millimeters of mercury. It doesn't matter in this particular gas law what our unit of pressure is. It very much matters what our unit of temperature is. Very much matters. Okay, Kelvin. Right? Always Kelvin. And we have Avogadro's law. At constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of gas. As moles, number of particles increases, so as you add more gas particles, what will happen to the volume of that gas? If it's in a container that's flexible, the volume of that gas will increase. Okay, so V1 over N1 is equal to V2 over N2, N being the number of moles. Now, you guys, I'm really rolling through this very, very quickly so that it's not just the longest video in the world, and I'm almost out of time before period 7 comes in. There are so many nuances about these things that we are going to talk about. One thing I do want to say, though, and I want you to write this down, that if you have 3 different gases, let's say, and those 3 different gases are at the same, you've got the same volume, they are at the same temperature, and they are at the same pressure. So you've got 3 separate containers of gases. Let's say 3 balloons because they are flexible. One is nitrogen gas, one's oxygen gas, one is water vapor, let's say. And they are at the same temperature, pressure, and volume. What you know, you guys, is that you have exactly the same number of moles of gas in each one of those balloons. Okay, make a note of that. Last but not least, you guys, I've already given you the ideal gas law. Keeping in mind here, let's kind of move that over so that we can actually see it this time around. That then this gas law takes into account all of the other individual gas laws. Okay, inversely proportional, directly proportional. Okay, so notice, you guys, we can always go to PV equals nRT to kind of figure that thing out. How is V and N, right? V1 over N1 is equal to V2 over N2. V and N, right? We're on opposite sides of the equal sign. Now, the one thing to keep in mind, remember, is that with the ideal gas law, because we are using the universal gas constant here to relate all of these quantities together, and the units for that are liter atmospheres per Kelvin mole, that our pressure has to be in ATM to use this thing. Our volume has to be in liters. Number of moles is number of moles. Our temperature has to be in Kelvin, but it's in Kelvin with all the gas laws, so that we can then tie all those things together with this value of R. That was really fast. Again, we will talk about the nuances of this so much more. Okay, that's it.